Hello and welcome to today's class. Good evening, Anumanta. Okay, today we are here for the ninth week of the problem solving section session for availability and management of groundwater resources. We will be focusing on problems that are that have been that are related to the lecture series from lectures 40 to 44, which is basically on estimation of total annual replenishable natural groundwater recharge. This and the I'm pretty sure that all these questions will be helpful in for you to do the assignment 9, and the ninth assignment is due by tomorrow, the 25th of September. So we'll move on to today's problem solving session. I'll be, like always, displaying some questions uh, in the screen, and we'll give you some time so that you can read through the questions and you can put in your answers in the chat box. And then after that, I'll be discussing the explanation related to the answers and what the other terms in the options and all include, which is going to cover whatever is taken in these lectures 40 to 44. uh, Around 80% of it is covered in these problem solving sessions, so it will be helpful as a revision also for you. So we'll move to the first question. Before I show the first question, let's discuss some concept based on which the first couple of questions are. So in this chapter, in this lecture series, there is a portion that involves talking about natural groundwater recharge methods. So some of the recharge methods, that is methods to naturally recharge groundwater resources, are what we'll be discussing now. One of the example is gully plug. Gully plug, as you see, is something like this. Yeah, so it is something like this, which is basically made from stones and boulders that you can find around this natural stream, and they make a bunt-like structure in this form, so that water that is coming from this side is collected, and it will recharge the groundwater resource in that area. And one important point, or one uh, key point in this in using this gully plug is this is mainly used when there's a natural break in the slope. So if you see in this picture itself, you can see that water is flowing, and then there is a break in the slope where water will then again go below than this level it is flowing in. So in places like these, there are such structures that are built which will help in accumulating water in here, and then it will help in recharging the groundwater in such locations. So local stones, clay and bushes across small gullies and streams, these are the materials with which these gully plugs are made, which these are all materials that are available locally. The next one is a contour bund. Contour bund is nothing but in places that has slopes of these nature, bunds will be constructed at specific intervals along the slope. So what happens is, when it rains, or when there's a runoff event, water will get collected in this area as well as in these areas, and then it will help in retaining the water there, which eventually will infiltrate and percolate and reach the groundwater. So this is helping in conserving the soil moisture in these areas to a long period of time, and this is particularly useful for regions having low rainfall where the monsoon runoff can be impounded by constructing these bunds. Now, the spacing between the bunds depends upon what is the slope in that area as well as the permeability of the soil in this area. Now, with soils that are having less permeability, the spacing will need to be closer. This is because we know that permeability is a property with which the water can flow within the soil, within an aquifer in a very easy manner. So once the permeability is lesser, this is also indicating that water, the time taken for water to enter the soil will be uh, a lot a longer time. It will take a longer time for water to enter the soil, as a result of which it is necessary that we place the bunds at closer intervals so that water can retain at more locations for a longer period of time. And this is why they say that in place, if it is a soil with lesser permeability, these bunds have to be constructed at a closer space, so that this is because flow of water within the soil will be less, so we have to control the runoff a little more higher than soil with a more with a higher permeability. So again here, this kind of recharge technique is suitable for lands with moderate slopes, uh, and terrace cultivation is not a very in places where terrace cultivation is not there, these method can be adopted. So some key points here is where these contour bunds are appropriate in areas with low rainfall, moderate slopes, and monsoon runoff can be impounded. No, this is the key point here will be areas with low rainfall and moderate slopes. And this is also one point that you can keep in mind. If the permeability of the soil is less, then the spacing between the two contour bunds will be closer. The next technique is the Gabion structure. Gabion structure, as you see over here, it is a structure that is built with a lot of rocks and pebbles and huge stones, and constructed in such a way that all these are stacked inside meshes at the banks of such streams and rivers. So what happens is when there is huge when there is a huge amount of rainfall, this stream is going to overflow and water is going to come into this area. Once the stream or the water level subsides, this water will be retained over here, and this water will help in recharging the groundwater in this area. So they are making use of the overflowing water, storing the overflowing water with the help of such structures, which will help later on in recharging the groundwater in this location. So that is what Gabion structure is. Gabion structure is here made by putting locally available boulders in a mesh of steel wires, and they're anchored to the stream banks. So this is what happens when this is the process that happens where Gabion structures are used. The process how natural recharge is occurring. Then there are check dams. Check dams are something that we're all familiar with. These are small dams that are constructed across small streams or rivers which are having a gentle slope. And these dams will obstruct water and help this water from the stream to contribute to recharging groundwater. Again, key point is gentle sloped streams, and they should have sufficient thickness of permeable bed to facilitate the recharge of stored water. So if this bed, if the soil there is less permeable, the water is just going to stay there accumulated. There's not much of recharge that is going to happen. So in order to accumulate the water that is flowing through this gently sloped streams, it is necessary that the bed of the stream also has soil that is highly permeable. So that are two key points in this kind of a structure. Which stage of check dam is preferred? Like further, that is depending upon the watershed and the stream and the characteristics of the land. Here we are just looking at some examples of what are the naturally recharging structures. We don't have to go into that many details. Okay, the next one is subsurface dikes. This is again a structure which is constructed at the subsurface level. If you have a stream, then across the stream, a structure is constructed such that the aquifer itself, water from the aquifer itself is accumulated and stored or obstructed, so that this itself is acting as a recharge to the surrounding aquifer. Then there's dug well recharge, which is also something that we are familiar with. Old wells or wells that are not contributing a lot, water can be stored in this in order to just for the purpose of recharging groundwater. Again, if it has to be recharged, you desilting chamber to the bottom of the well or below the water level, so that the silt or sand doesn't come out because of the force of the water. So these are some examples of natural ways of recharge. I don't think so. The lecture series goes deep into what dug wells are, what groundwater subsurface, and what are the sizes, and what is the design criteria and all. So you just need to know about some examples and generally where they are used. So the first question here is about these natural recharge structures. Which of the following is constructed across small streams having a gentle slope? Okay, so the correct answer is check dams. Uh, let's go back to gully plugs is used in small streams, and when they have a local break in slope to permit the accumulation of water. Whereas check dams are the ones that are talked about having built-in gentle streams. And if you see from the pictorial representation, these streams are a little bit larger than what is shown here. These are very small streams. And one key thing they're talking about here is a break in the slope. Whereas here it is right across the stream, which needs to be a little bit larger stream. I mean, comparatively to the other one. So the correct answer here would be check dams. Now we'll go into some methods that are used for estimating groundwater recharge. So there are three methods that are being discussed in the lecture series here. Groundwater level fluctuation method, groundwater balance method, and rainfall infiltration factor method. Now, groundwater level fluctuation method, it is based on what is the rise in the water table during the monsoon season, and it is estimated using this formula. This is giving us the recharge and basically recharge due to rainfall. So that is what is going to increase and decrease or fluctuate the water table. So rainfall recharge will be the sum of this term and this term. But here, this term is the product of the specific yield, which is dimensionless, and delta S, which is the change in the water level. Then here this term is the product of TP, which is abstractions during the rainy season divided by the study area. So if you're considering an area, what are the abstractions that are occurring in that area? Abstractions involve all those which is not contributing to the runoff. There is infiltration, there is depression storage, interception, through fall. All of that are coming under abstractions. Evaporation, evapotranspiration, all of that will be abstractions. So all of the abstractions together divided by the study area is what this TP term represents. And RT is the return flow due to any irrigation which will occur during the rainy season. So if there is a flow that is occurring as a result of irrigation, then the product of that as well as this subtraction divided by the total area will be what is considered over here. Generally, this RT is negligible, so this term tends to be zero when we see a bit problems in related to this. So this is one method. The next method is the water balance method. Here again, like we had studied about the water balance method, precipitate inflow minus outflow is equal to change in storage. It is the same in here, except that it is talking about the groundwater balance, and the other one includes all of the elements of water: surface water, groundwater flow, infiltration, everything. So here they're talking about groundwater, but the same thing is applicable here also. Whatever is flowing within a particular duration of time, whatever flowing out within a particular duration of time will give us if there is any change between these two values, it indicates that that volume is contributing to groundwater. Then there is another method called the rainfall infiltration factor method. Here, the recharge from rainfall during monsoon season is found out as a product of a rainfall infiltration factor, area where the recharge needs to be computed, and normal rainfall in monsoon season. Normal rainfall, we had discussed in the earlier classes about what normal rainfall is. It is the average annual rainfall, and this average is taken for a period of 35 years. So that is what is normal rainfall called. So that value multiplied by the area for which the recharge is to be computed by this infiltration factor, which will be provided to you if there's a problem that is related to this, which is actually rainfall infiltration factor is dependent on a lot of factors like the soil property, the vegetation, everything. So that. So these are the three methods that are used for estimating groundwater recharge that is being discussed in this lecture series. So here the question is, which is the correct equation to calculate groundwater recharge by rainfall infiltration factor method? Which formula out of this is the right formula? Okay, so the correct answer is answer A. The product of the rainfall infiltration factor area of computation area that is covering the computational region and normal rainfall that is occurring in the monsoon season. So that is the correct answer. Option A is the correct answer. Moving on to the next question. Here we're talking about a numerical problem that is involving the estimation of recharge. Here they're asking what will be the water level at the end of the month if this had an initial water level of 103.2 meter and during the starting of the month, and it is receiving 150 mm of water through infiltration, and some water is being extracted. Around 70 mm of water is being extracted. So what will be the final water level? This is a very simple arithmetical questions which you don't even have to know about the methods and all, but nonetheless you can just think about the methods that we discussed and use the appropriate method and find the answer for this very simple numerical. Please do this and post your answers in here. Okay, so let's just see what the solution is. So this is how it is solved. This is basically done using the groundwater balance method. We have an initial water level, and they're saying that there's a inflow, that is infiltration, which is basically water that is contributing to the groundwater. There is 150 mm of water going in through infiltration, but 70 mm of water is being extracted, so which is the outflow. So we need 150 minus 70, which will be 80 mm equal to 0.008 meter, which when added to this initial water level is going to give us the final water level. That is what is asked. By the end of the month, what is going to be the water level? So we'll add this change in storage to the initial level to get what is the water level at the by the end of the month. And here this option is what is the correct option for this 103.28. So once again, just brushing up through this, how this has been done. The inflow in here is the water that is contributing to the recharge, which is 150 mm, and the outflow is the water that is being removed from the from the groundwater, which is 70 mm. When you find the difference between it, the storage, whatever water is stored over there is 80 mm, which is 0.08 meters, and that when you add to the already existing water level, you will get what is the water level at the end of this month. So this is how this problem is done using the groundwater balance method. Moving on, fluctuation in water table is expressed by which of the following expression? Is it the sum of the water table in the post monsoon and pre monsoon divided by the average of that, basically? Or is it the difference between the water level during post monsoon and pre monsoon? Or is it the sum of it, or the half of the difference of it? Okay, I'll move on to the solution because this might need a bit of an explanation of the concepts in the lecture. So fluctuations in the water table, they are caused as a result of the precipitation between a lot of seasons and a lot of years. And basically, when we talk about groundwater flow, sometimes it's just 1 mm or a couple of millimeters in a year or couple of millimeters in months. So it is a very slow. It is something that gets recharged at a very slow rate. Flow is also happening at a very slow rate. So the fluctuation in water table is generally taken as the uh, difference between the water table in post monsoon season, which is nothing but the season that is after the monsoon. Monsoon happens between June to September, so it will be October to November or December. October to December is the post monsoon season, and pre monsoon season is just before the monsoon season, which is starting by June. So it will be March to May. So what is the water table immediately after the monsoon season, and what is the water table just before the monsoon season? The difference that between that is what is considered as a fluctuation in water table in a particular place, and it is measured in meters below ground level. So ground level will be taken as the reference level, and what is the depth below the ground level will be the value of this water table fluctuation. So the correct answer here is water table in the post monsoon season minus water table in the pre monsoon season, which is option B. Moving on. As per the assessment of the Ministry of Jal Shakti 2017, what is the amount of total annual groundwater recharge that has occurred? Again, this is something you'll only know if you've gone through the lecture series already. I think I'll just move on to the answer. So, according to the assessment that is conducted in 2017, and this assessment is carried by the central government and the state government's water board together. I think I'm not very updated with the latest assessment, but in the lecture series, they're talking about the assessment that has occurred in 2017. The total annual groundwater recharge here, not they're not talking about the groundwater available, but groundwater recharge alone that has happened is 432 billion cubic meters. And the yearly extractable groundwater that is available to us is 393 BCM. So, out of this 432 recharge that has happened, the one that can be extracted is 393 billion cubic meters. And the annual groundwater extraction for all uses is 249 BCM. Although we can extract this 393 BCM, out of that we can only use 249. Out of this 249, 89% of it is going for irrigation purposes, and only 10% goes for the domestic usage. So in three in 249 billion cubic meters of water that can be used from this annual extractable groundwater, 89% goes for major portion of it is going for irrigation, and only around 10 percentage is going for domestic use. So this percentage is a bit, I think I've seen it in previous years questions, so you can just keep note of this statistic over here. So the correct answer for this would be 432 billion cubic meters, which is option B. The total annual groundwater recharge is 432. The annual extractable groundwater resource is 393. And the actual water that can be used from this extracted water is 249. And 89% goes for irrigation, 10% goes for domestic use. So that was about this question. Moving on. How a confined aquifers recharge? Is it recharged by vertical infiltration? If this is this statement true or false? You can drop in your answers in the chat box. So here the question is basically about how these confined aquifers are being recharged. And here they are saying they are not directly recharged by vertical infiltration. So let's see how this how water is, how can we obtain water in or how does water reach the confined portion. So in case of unconfined aquifers, that is basically this top aquifer over here, which is not bounded by any confined layer, water is reaching, or the water table is formed as a result of infiltration and percolation of water from surface, vertical infiltration of water. But in the case of confined aquifers, which is confined by layers, there the end of this aquifer, which is going to be very far away from the location. Say if we have the confined aquifer in this location, the end of this aquifer is basically open to the surface, and it is an unconfined portion of the aquifer. So this confined aquifer, if it is starting from this region, water is going to vertically infiltrate into this unconfined portion, and then it is going to move towards this area, as a result of which confined aquifers are having the water. So actually the statement is true. It is not being directly recharged by vertical infiltration. Instead, the end of the aquifer, which is going to be a unconfined aquifer, is going to receive water as a result of infiltration, and then that water is going to move and contribute to the portions of confined aquifer. So this question here, the statement here is true. It is not directly recharged. Again, another question to estimate the groundwater storage or groundwater recharge. A small aquifer is 150 aquifer of area 150 hectare received 100 of water through infiltration over a span of 1 day. The water that is drained is at the rate of 1.5 meter cube per second. Find the change in storage in So we have the area here. We have some inflow data here. We have outflow data over here. And we also have time over here. So they are asking about the change in storage. So remember which equation is making use of the change in storage, and then appropriately use the estimation method to find out the answer. It would be good if you guys could do it and put in the answers, and then just blindly following the solution part would be like a revision also for you guys. So please try to do it. I hope you guys are doing the problem. Okay, so moving on to the solution. Here also we are using the groundwater balance method. Inflow minus outflow is change in storage. Only thing the values given are not very direct. So here we are talking about an inflow of 100 per day, and although this is just talking about the depth of infiltration, so but we also have the area over here. So what we do in order to get the discharge rate or inflow rate, we multiply this area into this depth to get the inflow rate. So here the area is 150 hectares. 150 hectares, when you convert it into meter square, you multiply it by 10 to the power 4 and you get this. And the inflow depth is 100 So you multiply this with this. When you multiply this and this, you get the inflow rate. Outflow rate is 1.5, or you can also um, you can do it anyways. You can multiply this and divide it by convert the days into seconds and do it, or else you can just find the volume. Here the outflow rate is 1.5 meter cube per second. So they are finding out what is the volume for 1 day. Here we have the volume for 1 day, inflow volume for 1 day. We have the outflow volume for 1 day. So net outflow is equal to, it's minus over here, not divided by, inflow minus outflow, which is equal to 0.0864 meters or 86.4 mm. Wait a second. I'm also confused why the answer is like this. Anyone, if you done the problem and got any other answer? If you've got any answers in the option, then that would be the correct one. Change in storage. I'm getting a totally different answer. Has anyone, if you have anyone of you done the problem? Suvarna, Arif, Hanumanta? Let me go through this problem once again. Oh, okay, they've asked in mm. Okay, so okay, makes sense, makes sense. Okay, makes sense. Okay, I was trying to find the answer in meter cube. Here, this value is going to be, just a second. When I provide the calculation, I'll provide you with the proper calculation. But here, yeah, here this is going to be 15,000 meter square, 100 mm. Okay, okay, area. Yeah, this calculation is right. Yeah, this calculation is right. I'm sorry, I'm the one who got confused. So here they have found out the area and they have used divided the volume by area to get the depth of outflow. We already have the depth of inflow here. So just minus this inflow minus outflow and you get 13.6 mm. So the water level is going to rise by 13.6 mm. I'm sorry, I got confused a bit over here. So please go through this problem on your own once uh, when you get the PDF of this file and the video also. So answer A, option A is the correct answer. Okay, next question. India is receiving rainfall for both what kind of monsoons? I mean, what are the two different types of monsoon season that we have in our country? It's southwest and northeast, or southeast and northwest, or southern and northern monsoon, or eastern or western monsoons. Okay, so the answer is A. We have two kinds of monsoons in our country, the southwest monsoon and the northeast monsoon. Southwest monsoons are the monsoons that give, I think typically 75% of the country gets its uh, or experiences strong monsoons because of the southwest monsoons, and the remaining 25 to 30 percentage is experiencing monsoons because of this northeast winds. So the correct answer is option A, southwest monsoon and northeast monsoons. Which period in India is considered to be pre-monsoon? We know monsoon, there are four seasons in a country: monsoon, post-monsoon, winter, monsoon, winter, summer, and I'm sorry. After monsoon, you have the post-monsoon, then you have winter, pre-monsoon, and then again monsoon. So, what is the pre-monsoon period? If you know what is the monsoon period, you will be sure about the pre-monsoon period. It's something we need to, as part of, if you are associated with water resources, is some basic thing that we'll have to know about the seasons and the water year and all that. So let's just go to the solution. So according in our country, we are having four kinds of seasons. One is the monsoon. Monsoon season is extending from June to September. After that, we have the post monsoon. Some people call it the autumn season, but generally, when we talk about the seasons, term post monsoon is used. So after the monsoon season, post monsoon season extends from October to November. Then there's a winter period that is extending from December to February. Then there's the summer or the pre monsoon period that is basically from March to May. Then again, June to September, we have the monsoon season. So monsoon is a period from June to September. June, July, August, September, 4 months. After that, from October, November, we call it post monsoon. Then December, January, February is winter season. Then March, April, May is summer season or pre monsoon. Class one. So the correct answer for this, here they have asked about pre-monsoon period. Pre-monsoon period is basically from March to May. So here April, May is the option that is given. So you can say it is this option too, because April comes between March to May. Next question, which out of the following is not a method to estimate groundwater recharge? So we had talked about three methods of groundwater recharge. Which out of this is not a method of groundwater recharge? Okay. So let's move to the answer. We had talked about groundwater level fluctuation method, groundwater balance method, and rainfall infiltration factor method. Thiessen's polygon method is to calculate the average mean rainfall. It is a method of estimating mean rainfall, not groundwater. So the option C is the correct answer. Now this numerical calculate the groundwater, calculate using this groundwater level fluctuation method. Um, the specific yield is given, effective change in water level is given, return flow is said to be negligible. So what will be the R term? The formula is what? I'll write the formula in here. It's R is equal to specific yield into effective change in water level. Effective depth. I don't remember the term. It is depth. Sorry. Depth plus TP into R, where R is the return flow due to irrigation, TP is the abstractions divided by the area, D is the depth, effective depth, and SY is the specific yield. Please try to do the problem and put in your answers in here. Again, since return flow is negligible, it is going to be equal to 0. So this term is going to be 0. You just have to calculate these two products. Okay, so this is a pretty direct question. So I'll move on to the answer. So according to the formula, it is Sy into delta S. Sy is a specific yield, delta is the effective change in water storage, Tp is the abstractions divided by area, Rt is the return flow. Since Rt is negligible, it is considered as 0. So 0 into Tp, this whole term is going to be 0. Sy into delta S, Sy is given as 0.09, delta S is given as 50 centimeters. So multiplying these two terms will give 4.5 centimeters as the answer. Simple problem, direct substitution. You can go through these slides again to revise this question as well as the groundwater balance technique too. Okay. Now, like we had talked about the various seasons. So in India, the water year, basically, when we talk about how much rainfall our country has received, we consider that year as the water year. I mean, the period during which we take the measurement as a water year. And the water year in our country starts from May 31st till the next year, May 31st. So that is why, because June is the month during which the monsoon starts. So the water year in India is from May 31st to June 1st to May 31st in the next year. That is considered as a water year. So when we talk about rainfall per year, it is not from January till December, but instead it is from June 1st to next June 1st. Now, same like having a water year, we also have something called a groundwater year. So when we talk about water year, it is talking about all the rainfall that we are obtaining because of the southwest monsoons as well as the northeast monsoons. It's not just isolated to one kind of monsoon, but in the case of groundwater year, uh, June to August, and the southwest monsoon is from June to August, and August September is the northeast monsoon. Um, this water year is considered as the beginning of the commencement of the predominant monsoon. Say for certain regions, like I said, 75 to 80% of a country is receiving its main rains from the southwest monsoon, and some regions are receiving from northeast monsoon. So those regions that are obtaining rainfall as a result of southwest monsoon, their groundwater year is going to start with 12 calendar months beginning from the commencement of the southwest monsoon. So southwest monsoon are consistent during June to August and northeast monsoon from October to November. So for places where rainfall is mainly because of this northeast monsoon, their groundwater year is going to start from the September 31st till October 1st to September 31st. Similarly, for these regions that are obtaining rainfall from southwest monsoon, their water year is going to be from June 1st to May 31st. So it is not about the entire rainfall, it is about the rainfall which is the predominant season of rainfall that is contributing to rain in that region. So groundwater year for purposes of groundwater assessment is consisting of 12 calendar months beginning from the commencement of the predominant monsoon, which is the most important term here. It is not fixed. It for some regions it is a particular period. For other regions it's a particular period where the months differ. 12 months will be there, but the months will differ. So this is one important concept that is being discussed in this lecture series, the groundwater year. Now, apart from that, again, the groundwater year can be subdivided into two seasons. One is the monsoon season and non-monsoon season. Monsoon season is the season where the commencement of the predominant monsoon and a month after it stops. So the monsoon will start, and then uh, when a month after this monsoon stops is called the monsoon season in a groundwater year, and non-monsoon season is the rest of the groundwater year that doesn't come under this. Again, monsoon season is going to be different months for the areas receiving southwest rainfall and different for northeast rainfall receiving area. So groundwater, we know what is groundwater year. We also know what are the seasons within a groundwater year. Two things, monsoon season and non-monsoon season. Then there is pre-monsoon and post-monsoon intervals. Um, this is the periods during which water level will be measured. I think we discussed water in the post-monsoon season minus water in the pre-monsoon season is what the what groundwater level fluctuation is measured in this way. So these two intervals are called pre-monsoon, post-monsoon. Water in the post-monsoon minus water in the pre-monsoon is what will give us the water level fluctuation, groundwater level fluctuation. Okay. Then there is something called the groundwater assessment year. So in a groundwater, in a lot of groundwater years, the year during which the groundwater assessment has been conducted is called the groundwater assessment year. We had talked about 2017 when we had just talked about a lot of statistics. There is annual replenished recharge groundwater, total extractable annual recharge. This happened in 2007. So that year it can be called as a groundwater assessment year. a lot of things, components of the groundwater draft, recharge, then the recharge from rainfall. A lot of that is considered, a lot of assessment is conducted. So that is the difference between groundwater year and groundwater assessment year. Groundwater assessment year, out of a lot of years, when is this report being made is called the groundwater assessment year. Groundwater year is the period of 12 calendar months, that is starting with the predominant monsoon season in that particular area. Under groundwater year, there are two seasons, monsoon and non-monsoon season. Monsoon season is the period extending from the starting of the monsoon till 1 month after the monsoon ends. And non-monsoon is the rest of the season. Pre-monsoon and post-monsoon intervals are there during which the water levels are measured. So these are some of the important points in this 4 slides that we have discussed. So again, which out of the following is considered as a groundwater year in India? Please drop in your answers in the chat box. No answers? Okay, it is the option. No, it's option A. 12 calendar months beginning with the commencement of the the dominant monsoon or predominant monsoon. Now, what does groundwater assessment year mean? This is also something that we discussed in the earlier slides. Yeah, correct answer. It's option C, groundwater year when the groundwater assessment is made. So again, we studied about what is groundwater year, what are the seasons in groundwater year, what are the periods during which the measurements are made, and what is a groundwater assessment year. Now again, based on the type of natural recharge method, what type of recharge method involves using boulders and steel meshes? Okay, correct answer. It's gabion structure. These steel meshes, there are big stones that are placed inside the steel meshes, and these are called gabion structures. So correct answer is option D. Now, what is a mathematical expression to calculate the groundwater development in percentage? I think I'll just go with the explanation because you might not be familiar with these, or give it a try. If there are people who know, give it a try. Okay, yes. So let's just see. There's something called the concept of TARR, for the sustainable development of groundwater, and there are various steps to this. In first, the total annual replenishable recharge, which is estimated in million meter cube per year. The step one is to calculate the specific calculate TARR using this formula: area into what is the average water table fluctuation into specific yield, and specific yield can be obtained using this formula. I don't think so doing this entire computation will be required, but then they might ask you some questions like these ones: what is the first step in estimating TARR, area into average water table fluctuation into specific yield. And specific yield is obtained from this formula, which involve to be functions of annual rainfall in millimeter per year, annual groundwater runoff, annual surface runoff, and the water table fluctuation. So all of these will help in obtaining the specific yield. That multiplied with the average water table fluctuation and area will give the first step of computing uh, total annual replenishable no, sorry, this is total annual replenishable recharge. Then they are computing it using the rainfall infiltration factor method, and then finding the average um, total annual replenishable recharge. So first they are computing using the groundwater fluctuation level method, and second they are calculating using the rainfall infiltration factor method. Then they are finding the average of these two methods. Step 3 is estimated draft to mine discharges must be equal to given in equation. The annual domestic water withdrawal in that area. Now this is about the recharge that is happening. Here we'll compute the water demand or water consumed. That is population by consumption rate into number of days. After that, the net draft will be the average TARR that has been computed over here minus the estimation that is done, which involves the outflow, that is the removal of water or the consumption of water, estimated draft through mine discharge and domestic draft together. After that, the groundwater development percentage is the net draft by average TARR into 100. The net draft is some value that will be given, I suppose. Yeah, this value. Net draft by average TRR will give us a groundwater development percentage. So this, I don't think so there'll be big problems that comes involving you to do all of the steps. Even if it comes, I think it is not a very complicated. It's just because there are a lot of steps involved and there's this equation involved, which seems a bit tedious to uh, remember. But otherwise it's kind of okay. But again, give a little focus on this equation, net draft, and how do you get the net draft and how do you get the average TAR, and what is this groundwater development percentage. So here the option C is the correct answer, like a few of you said. Net draft by average TAR into 100. Okay, this is again relating to the seasons in our country. In Indian conditions, which of the following months is considered to be post-monsoon period? So I did talk about what is monsoon, post-monsoon, winter, and pre-monsoon. Okay, so I've got one answer. Okay. Okay, so it is correct. It's October to November. Let's just go through the seasons once again. Monsoon is June to September. Post-monsoon is October to November. Winter is December to February. Pre-monsoon is March to May. So here they are talking about post-monsoon period, which is October to November. So correct answer is option A, like few of you posted. Now, which type of aquifer is directly recharged by local rainfall and rivers? We had already dealt with the question that is associated with this. So, which aquifer? Is it a confined aquifer? How does it get recharged? Unconfined aquifer? How does it get recharged? Okay. So it is the unconfined aquifer. Like I have told earlier, through vertical discharge that is occurring as a result of rainfall. Unconfined aquifers are the ones that get recharged directly because of this rainfall. Whereas confined aquifer, the end portion of a confined aquifer, somewhere there will be an unconfined portion that gets the recharge, and that is what is contributing to the confined water in the confined portions. So the correct answer is option B, unconfined aquifer. These are being recharged directly rainfall and sometimes from rivers also. We studied about influent rivers and influent and effluent streams. So influent streams will provide water into groundwater. So these are basically recharges that happen in unconfined aquifer. Now, this is about groundwater assessment unit. So, we had talked about groundwater assessment year, groundwater year, and what are the seasons in that. Now, the area is also divided into units so that these assessments can be conducted based on the topography of the area, or maybe there are a lot of factors based on which the regions are divided into areas for ease of assessment. So some of that is mainly they are divided into block, taluk, mandal, and watershed. So these are the major separations, the main segregation of area for groundwater assessment. Now there are also sub-units within these blocks, taluks, mandal, and watershed. That is based on the terrain of that area. So that first is the hilly area, then there is a poor groundwater quality area, command area, and non-command area. So in every block or every taluk or every mandal or every watershed, these subcategories are also uh, areas are also divided into these subcategories. So what is a hilly area? These are areas that have slopes that are greater than 20 percentage. Then groundwater potential, there is good groundwater potential in these hilly areas. uh, the recharge is practically negligible, so there is no groundwater assessment made over here, because although they might have a lot of groundwater, recharge level is very low. So three key points to take away in this hilly area is these are areas that are having slopes greater than 20%. These are having good groundwater potential, although the recharge is very negligible. So no groundwater assessment is not conducted generally for hilly areas. Then there is a subunit of poor groundwater quality area. Groundwater recharge and all is happening, but the quality is bad. The quality might be below the groundwater quality will have some contamination or pollution issues. So again, areas that are associated with these saline groundwater, that comes into this category. So hilly areas is based on the slope and the potential and the recharge level. Here also recharge is very high, but the quality of water is going to be bad, and that is pretty obvious from the name of this subclassification. Now, command area is those portions where the groundwater quality is very good, and also there's a lot of agriculture, the cultivable area that is coming under this. irrigation is occurring in these areas. So here, good groundwater quality, unlike the previous category, and okay. But then again, yeah, we said that these areas have good irrigation. These areas are ones that are coming under uh, surface water irrigation, well irrigated areas. But um, isolated pockets that are less than 100 hectares, which is being irrigated with surface water resources, should not be considered as one criteria for this command area. So those are 2 or 3 takeaway points for command area. Then there is again non-command area. Again, there is good water quality, but then areas under the command of tanks and ponds, which are only localized pockets less than 100 acres, should also be included. So here they are not including pockets that are less than 100 hectares, but in this, under this area, they are including this portion which is neglected in the command area. So non-command area is a portion where irrigations for regions less than 100 hectares is also included. So in the groundwater assessment unit, which subunit is comprising areas with ground slopes greater than 20% and practically negligible groundwater recharge? It is the hilly area. So option D is the correct answer. Now, which category of groundwater subunit has practically no scope for any future groundwater development? Maybe you can just go by the names. Is it safe, semi-critical, overexploited, or critical? Groundwater subunit that has no scope for groundwater development. Okay, so let's go into again further subcategorization of command and non-command area. So first we saw there is a general classification of the assessment units that includes blocks, taluk, mandal and watersheds. Within that itself, based on the terrain, based on the quality of water, there is hilly area, poor groundwater quality area, command and non-command areas. Apparently, this command and non-command areas are the ones which have good quality water. Recharge is also sufficient. So they are a little more important in comparison to the other two. So there are again some subcategorizations for command as well as non-command areas. And those are safe, semi-critical, critical, and overexploited. So let's just go through what all these are. So safe is a subunit of the command or non-command command area where the potential for future groundwater development is really good, because the groundwater, the stage of the, they're talking about the potential of groundwater development. Although the present condition of groundwater development is less than or equal to 70%, and water table during at least one of the two intervals, that is either pre-monsoon or post-monsoon, is showing a declining trend. So although it is not showing a complete declining trend in the water level, there will be a decline in trend for either the pre-monsoon or a post-monsoon season. The groundwater development is equal to or less than 70%, but in general, it has a potential for good groundwater development. Then again, there is a category. The stage of groundwater is greater than 70%, but less than or equal to 90%. It is coming between 70 and 19%. Here, there is no falling trend. The subunit, if it is categorized as safe on the basis of the criteria mentioned in B, it is to be noted that okay, not important. So even under safe category, there are two categorization. One less than 70%, equal to or less than 70%, and another between 70 and 90%. Here there is a decline that is seen in the trend of water table fluctuation. Here there is no decline seen. So all these areas are, I mean, if these areas are exhibiting these potential of groundwater recharge, groundwater development, you can categorize that area as a safe area. Now, semi-critical area, again, what the stage of groundwater development is greater than 70%, less than 90%, but and the water table during only one of the intervals is showing a falling trend. So the difference here is this is less than 70% and a decline. Here this is between 70 and 90%, but no decline. But in semi-critical, it is between 70 and 90 percentage, but there will be a falling trend. And then again, um, under semi critical, the rainfall recharge during the monsoon season, uh, the trend of the water table can be evaluated. Okay, so this is what semi-critical area basically means. It is when this region's groundwater development is between 70 and 90 percentage, and there is a decline at least during pre-monsoon or post-monsoon season. Moving on to what is a critical type. This is going to be the scope of groundwater development is very marginal. In this case, there is good scope of groundwater development, but again, it is not as good as the safe one. Critical is when the scope of groundwater development is almost very low. It is a borderline. Here, the groundwater development is more than development stage of groundwater well is more than 90 percentage, and water table during one of the two interval is showing a falling decline, or less than or equal to 100 percentage. Water table during both are showing a falling decline. So when we are talking about the groundwater development, it is that formula that we had discussed earlier, net draft by average total annual replenishable recharge. So if that value is more than 90 percentage, but there is a decline during one of the season, or if that value is equal to or less than 100, but both period there is a decline, then these categories and all come under the critical category. Then there's the overexploited category. There is no scope for any future groundwater development. Again, this is the stage of groundwater development more than 100 percentage. Water table during both are showing a falling trend. So these are things that you will have to go through again and keep in mind. It's a bit confusing because all of them are categorized based on the same criteria. So which is for which is something that you might need to memorize or find a link to study. But again, as the name suggests, safe, semi-critical, critical, overexploited, it is in that level that the potential of groundwater recharge is possible in these areas. So the category of groundwater subunit, which has no scope for any groundwater development, is overexploited. Critical, its marginal potential. Semi-critical, potential is there, but it has to be exercised with caution. Safe is when there is a huge potential for groundwater development. This would be the last question for today. Which of the following factors are contributing significantly to groundwater recharge apart from precipitation? Okay. So the correct answer is seepage from canal system. All these are not, atmospheric condensation doesn't contribute to uh, recharge. Desalination process is a totally different. Ocean tides are also not contributing to groundwater recharge. It's basically the seepage from canal system. When there's no proper lining that is provided on canals, water will go through these canals and it will recharge the groundwater. So this is also one artificial method of groundwater recharge, which we'll be covering in the coming sessions. So that's all for today's sessions. If there's any doubt, you can ask, or we can end the session for today. I mean, you're free to leave the session if you don't have any doubts. And before leaving, I would like to say that from the next session onwards, we'll be doing a revision of the next will be the 10th session. After that, we just have 3 more weeks. So we'll be covering portions related to assignment 1 gradually in the next 4 class, along with the 10th, 11th, 12 weeks session also. So that is an information that I need to share in this class. So thank you for attending today's session. If you have any doubts, feel free to ask. Otherwise, you can leave the session. These are going to come in the artificial recharge techniques. That is going to be in the next week. So I think I'll take it during that time. Thank you. Thank you. Thank you, Anvanta. Muthuram, do you have any doubts? If you don't have any doubts, you are free to leave the session.